the arrangement described, where 3 ground wires are spliced together with a common wire nut, 1 wire going to the fixture, 1 back to the main panel, and the third to a downline fixture controlled by the same switch, is a violation of the National Electrical Code, specifically the 1999 edition. This is because the grounding continuity is dependent on the fixture being connected. If the fixture is disconnected or removed, the grounding continuity to the downline fixture is interrupted. National Electrical Code 1999 Section 300.13 states the continuity of the equipment grounding conductor shall not rely on a connection within a device, such as a receptacle, a switch, or a similar device. The National Electrical Code requires grounding conductors to form a continuous path from the source of power to all grounded components and equipment. In this case, the fixture is relied upon to maintain the grounding connection to the downline fixture, which is not acceptable. A proper arrangement is to use a ground bar or junction box to connect all 3 ground wires together. This ensures that the grounding continuity is maintained even if one of the fixtures is disconnected or removed. To further clarify the importance of proper grounding and the implications of the described violation, let's delve deeper into the principles and requirements outlined in the National Electrical Code. Grounding is a critical safety measure in electrical systems, designed to protect individuals and equipment from electrical shock and damage. The equipment grounding conductor, often referred to as the ground wire, provides a low impedance path for fault current to return to the source. This low impedance path facilitates the rapid tripping of overcurrent protected devices, such as circuit breakers or fuses, in the event of a ground fault. The purpose of this rapid tripping is to quickly de-energize the circuit, preventing prolonged exposure to dangerous voltage levels and minimizing the risk of electrical shock or fire. When grounding continuity is interrupted, as in the described scenario, the effectiveness of this safety mechanism is compromised. If a ground fault occurs in the downline fixture when the primary fixture is disconnected, the fault current may not have a lower impedance path back to the source. This can result in a significant voltage potential on the metal parts of the downline fixture, creating a dangerous shock hazard for anyone who comes into contact with it. Furthermore, the delayed tripping of the overcurrent protective device can lead to overheating and potential fire hazards. The National Electrical Code emphasizes the importance of maintaining a continuous and reliable grounding path throughout the electrical system. Section 250 details the specific requirements for grounding and bonding, including the sizing of grounding conductors, the methods of connecting grounding electrodes, and the requirements for equipment grounding. The requirement in Section 300.13, which prohibits relying on a device for grounding continuity, is a specific application of these broader principles. The intent is to ensure that the grounding path remains intact regardless of the status of any individual device or component in the circuit. In the described scenario, the use of a wire nut to splice the 3 ground wires together is not inherently a violation in itself. Wire nuts are commonly used for making electrical connections, including grounding connections, provided they are appropriately sized and installed according to the manufacturer's instructions and the requirements of the National Electrical Code. The violation arises from the fact that the wire nut connection, in this particular arrangement, creates a situation where the grounding continuity to the downline fixture is dependent on the presence and connection of the primary fixture. To rectify this violation and ensure compliance with the National Electrical Code, the proper arrangement would be to use a ground bar or junction box. A ground bar is a metal bar specifically designed for making multiple grounding connections. It provides a central point for connecting all grounding conductors in an enclosure or panel. A junction box is an enclosure used to house electrical connections, providing protection and strain relief for the wires. When using a ground bar or junction box, each of the 3 ground wires, the wire from the primary fixture, the wire from the main panel, and the wire from the downline fixture, would be individually connected to the ground bar or to a grounding screw within the junction box. This creates a parallel grounding path, ensuring that the grounding continuity to the downline fixture is maintained even if the primary fixture is disconnected or removed. The ground bar or junction box should be properly bonded to the metal enclosure or panel, providing a low impedance path to ground. In addition to the physical connection of the grounding conductors, it's important to consider the sizing of the grounding conductors. The National Electrical Code specifies the minimum size of equipment grounding conductors based on the size of the overcurrent protective device protecting the circuit. This ensures that the grounding conductor is capable of safely carrying the fault current back to the source without overheating or causing excessive voltage drop. The grounding conductors should be properly identified with green insulation or green tape, indicating their purpose as equipment grounding conductors. The connection should be made using approved connectors or terminals, ensuring a secure and reliable electrical connection. It's also important to visually inspect the grounding connections to verify that they are properly installed and free from any damage or corrosion. In summary, the described arrangement of grounding wires, where the grounding continuity to a downline fixture is dependent on the connection of a primary fixture, is a violation of National Electrical Code 1999 Section 300.13. To correct this violation, a ground bar or junction box should be used to create a parallel grounding path, ensuring that the grounding continuity is maintained even if the primary fixture is disconnected or removed. Proper grounding practices are essential for electrical safety and should always be followed according to the requirements of the National Electrical Code. Furthermore, to expand on the understanding of grounding systems and why such arrangements are deemed unsafe, let's consider different types of grounding systems and their functionality. There are primarily two types of grounding systems: equipment grounding and system grounding. System grounding involves grounding the neutral conductor of the electrical supply system, typically at the service entrance. This provides a stable reference point for the voltage and helps to limit voltage surges. Equipment grounding, on the other hand, involves grounding the non-current carrying metal parts of electrical equipment, such as enclosures, raceways, and appliance frames. This is the type of grounding that is relevant to the described scenario. The purpose of equipment grounding is to provide a low-impedance path for fault current, as previously explained. The National Electrical Code provides detailed requirements for both system grounding and equipment grounding, ensuring that these systems are properly designed and installed to provide adequate safety and protection. When inspecting an electrical system, it's important to verify that both the system grounding and equipment grounding are in compliance with the National Electrical Code. This includes checking the grounding electrode system, the grounding conductor connections, and the bonding of metal parts. In addition to the specific violation described in the question, there are other common grounding violations that should be avoided. One common violation is the use of a water pipe as the sole grounding electrode. While water pipes are often used as part of the grounding electrode system, they must be supplemented by another grounding electrode, such as a ground rod or ground plate. This is because water pipes can be susceptible to corrosion or disconnection, which can compromise the effectiveness of the grounding system. Another common violation is the failure to properly bond metal parts together. Bonding is the process of connecting metal parts together to create a continuous electrical path. This is important to ensure that all metal parts are at the same voltage potential, preventing the possibility of voltage differences that could create a shock hazard. The National Electrical Code specifies the requirements for bonding different types of metal parts, such as metal conduits, metal enclosures, and metal piping systems. When inspecting an electrical system, it's important to check the bonding connections to verify that they are properly installed and secure. It's also important to be aware of the changes and updates to the National Electrical Code. The National Electrical Code is revised and updated every 3 years, reflecting advancements in technology and changes in safety standards. It's important to stay current with the latest edition of the National Electrical Code to ensure that electrical systems are designed and installed according to the latest requirements. Electrical codes can vary by local jurisdiction, and electrical inspectors are going to apply these codes. These are for safety of people and property. There are continuing educational opportunities available. Training is provided to ensure that contractors stay informed. These courses can cover new technologies and the most recent updates to the National Electrical Code. These resources are available to learn how to ensure electrical safety and code compliance. As for the topic at hand, and a further summarization is that the original wiring configuration relies on a light fixture to maintain grounding continuity. This setup means that if the fixture is removed or disconnected, the grounding to the downline fixture is interrupted, creating a potentially dangerous situation. The National Electrical Code explicitly prohibits grounding systems that depend on devices like receptacles or switches for continuity. The best practice is to use a junction box or a grounding bar. These allow for the independent connection of each ground wire, ensuring a continuous grounding path regardless of the state of any single fixture. When correcting such a wiring issue, ensure all connections are tight and corrosion-free. Use appropriately sized grounding conductors as specified by the National Electrical Code, which is based on the size of the circuit's overcurrent protection device. Mark the grounding wires with green insulation or green tape to clearly identify them. This correction not only brings the wiring up to code but also significantly enhances the safety of the electrical system by providing a reliable path for fault currents, reducing the risk of electrical shock and fire.